All right, let's go ahead and see what our interval convergence is here. So ratio test. Do the limit as n goes to infinity. The an plus 1 term, which is x minus 5 to the n plus 1 over the square root of n plus 1 times 3 to the n plus 1 plus 1. And then multiply by the reciprocal of that. So we have the square root of n times 3 to the n plus 1 over x minus 5 to the n. And we do definitely need the absolute values around all of this. And then it's just a game of grouping the like terms. So I think you can show not a lot of work here, but I would probably show the following work. I would write this as the limit as n goes to infinity of the absolute value. X minus 5 to the n plus 1 over x minus 5 to the n is just x minus 5. 3 to the n plus 1 over 3 to the n plus 2, we're going to get a 3 in the denominator. And then n to a power ends up not being contributing anything, right? We're going to write this as square root of n over square root of n plus 1, or even if you like, the square root of n over n plus 1. But when we take the limit, that's just going to be 1, that part of it, I should say. So when we take this limit, we're going to get just the absolute value of x minus 5 over 3. And that's going to be less than 1. And then you can either write the inequality first, multiply both sides by 3 first, kind of whichever way you want to go. I would probably write the inequality first. So I'm going to write x minus 5 over 3 between 1 and negative 1, multiply everything by 3, add 5, you get negative 3 plus 5 less than x less than 3 plus 5. So we have x between 2 and 8. Couple observations, our center is 5, our radius is 3. And technically, since the question said find the interval of convergence, we have to check the endpoints. If it just said find the radius, be like, great, the radius is 3, no need to check the endpoints. But if they say interval specifically, that is the question I would always ask in the future. We got to check the endpoints. So endpoints, we're going to check x equal to 8. Oh, I should be more thoughtful here, but oh no, that's the right way to go. So just as a reminder, last time I said, if you have a choice between picking one or the other, try to pick the one that makes it non-alternating first. It's just useful. So here's what I mean. So if I pick x equal to 8, I'm going to get a positive 3 to the end. So it's not going to alternate when I plug that in. So I'm going to get the sum from, I didn't even have to start say from n equals 1. From n equals 1 to infinity of 3 to the n over the square root of n times 3 to the n plus 1, which becomes just the sum from n equals 1 to infinity of 1/3 times 1 over the square root of n, or n to the 1/2. And that definitely diverges by the p-test. And the reason I point this out is because now when we do the next one, if it's alternating, which it probably will be, we can't just throw the absolute convergence test at it because we know it won't converge absolutely because the non-alternating version of it diverged. So if it's alternating, we will have to use the alternating series test. Yeah, but in fact, let me write this down and then I'll say more things. So if we plug in x equal to 2, we're going to get the sum from n equals 1 to infinity. 2 minus 5 is negative 3 raised to the nth power. Negative 3 to the n over the square root of n times 3 to the n plus 1. I'm going to break this up just a little bit to make it a little easier to see what I'm talking about. So negative 3 to the n is really negative 1 to the n times 3 to the n. And the denominator is the square root of n times 3 to the n times 3. The 3 to the n's cancel. Why I broke it up that way. And now what I've got is basically the same thing I had up above, except it's alternating. With the sum from n equals 1 to infinity of negative 1 to the n times 1/3 times 1 over the square root of n. Now, if this previous one had converged, I would just say, well, great. This thing is the same as that, so it's alternating. So it's also going to converge by slapping absolute values around it. And so I can say it converges by the absolute convergence test. But since this thing diverges, I can't do that. So I know that's not viable, and I'm just going to move straight to saying it converges probably by the alternating series test, or really throwing the alternating series test at it and seeing what happens. On the other hand, if this had been convergent, I would just be like, great, that converges too. Because absolute value of this converges because it's that, so this converges. So that's usually why I try to look at the one that's not alternating first, because if I know that one converges, I can save myself some work on the other endpoint. So here, this definitely does converge by the alternating series test. We can see it meets all the criteria, it alternates, the limit of the sequence is 0, and the terms definitely get smaller, or it's decreasing. So then we can say our interval convergence is +2 inclusive to +8 exclusive. Cool. I would imagine there'll be something similar to this on your first exam, but I don't actually. All right, let's look at Taylor's theorem. So far what I would say is to find a power series for a function, mostly we've just tried to make it look like 1/1 minus something to make it look like a geometric series. So far we have used / manipulated geometric series to express functions. I.e. how 1/1 minus x is equal to 1 plus x squared, and so on and so on and so on. But not every function looks like 1/1 minus x, or has a derivative or an antiderivative that looks like 1/1 minus some stuff. So if our function doesn't look like that, our function doesn't look like that, like something geometric or something that can be manipulated to be geometric, well, then we have another thing. Can we still write the function as a infinite series? And I will say the answer is generally yes, although technically not always. There are some strange examples, maybe not strange, but there are examples of functions that have a Taylor polynomial, but they don't actually equal their Taylor polynomial, which is kind of a weird thing to see. I wouldn't be surprised if Casals talked about it. That seems kind of like the guy he is, but let me know if you hear about that. So here is Taylor's formula. And I do definitely recommend memorizing it. Taylor's formula just says we can write our function f of x as, I like to write out the long way first, so f of c plus f prime of c times x minus c to the first plus f double prime of c over 2 factorial times x minus c squared, and it just keeps going on. The third derivative at the center over 3 factorial times x minus c to the third, and on and on and on and on. And the condensed formula, the summation sigma notation, is the sum from n equals 0 to infinity of the nth derivative at the center times x minus the center to the nth power over n factorial. That is Taylor's formula. What it says is, if you can find all these derivatives of your function, plug in the center, divide them by n factorial, multiply them by x minus the center to the power, that is going to give you an approximation of your function. I will point out, there's an excellent video that really explains this. I think it's on, I think it's 3 blue, 1 brown. I know Casals referenced it on his webpage somewhere. I think I might have posted it in Canvas already. If I haven't, I definitely will. I really recommend watching it. I mean, it's done well, but it also kind of makes it really easy to see why this really works. But the real idea here is basically this formula. If you look at this formula, the function f of x is going to evaluate, and every one of its derivatives is going to evaluate correctly at the center C. So what I mean by that is, look at this. If I plug in, just for example, f of c on the left is going to equal f of c plus f prime of c times 0 plus f double prime of c times 0, right? All the other terms are going to be 0. So, but then that's also true for any derivative. So if I take the derivative of both sides, well, f prime of x is going to equal the derivative of a constant, just a constant. Sorry, F prime of C, I'm plugging C, sorry. If I plug in C, I have to take the derivative first. This is where things get a little bit annoying. Sorry, so this is where I would say, yeah, fine. I walked myself into this one. So you take the derivative of this derivative of x minus c is just 1. So you're going to get 0 plus f prime of c times 1. The derivative of this is going to be f double prime of c over 2 factorial times 2 times x minus c to the first, etc. You plug in the center, you get just this because every other term becomes 0. So the whole idea with this Taylor's formula giving you this function is essentially saying the first derivative, the second derivative, the third derivative, every derivative of this function is going to evaluate the same way at the center as Taylor's formula does. And then as you move away from it, the approximation becomes less amazing, but still good. Now, do we need to know all that? Again, I think watching that video is useful. Well, how do we apply it? Well, the kinds of questions we usually get asked are, say, to find the first for non-zero terms of the power series for f of x equal to 1 over x squared, centered, and c equal to 2. Sorry, I can't see that. I will point out when we're trying to find just the first x number of terms, we don't have to be super focused on trying to find it. Whereas on the other hand, if they're asking us to find the entire summation notation for something, we typically do need to look for the pattern. And we'll get more into that in a minute here. So let's see, we're going to find our function. If I just start writing out the first few terms, is going to be f of c, so f prime of c times x minus c, double prime of c over 2 factorial times x minus c squared. And assuming all these terms are not 0, that'll be enough. These first 4, hopefully non-zero terms. If they're not all non-zero, then we'll add on at the end. So all I'm really going to do is I'm going to start finding derivatives. So I'm going to say, well, okay, great. My function is x to the negative second. My first derivative is going to be negative 2x to the negative third. My second derivative is going to be positive 6x to the negative fourth. And my third derivative is going to be negative 24x to the negative fifth. And then I need to plug in my center, which is given to me. So f of 2 is going to be 2 to the negative second, or 1/4. F prime of 2 is going to be negative 2 times x to the negative third, so 2 to the negative third, which is going to be negative 1/4. Double prime of 2 is going to be 6 times 2 to the negative fourth, which is 6 over 16, or 3 over 8. And finally, the third derivative of 2 is going to be negative 24 over 2 to the fifth, negative 24 over 32, which reduces to, I don't know, what does it reduce to? 4 and 3, negative 3 over 4. And then we could write out the Taylor, the fourth degree, or I should say third degree Taylor polynomial. So now we're going to get that f of x, our function, 1 over x squared, is equal to f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 over 2 factorial times x minus 2 squared plus f triple prime of 2 over 3 factorial times x minus 2 to the third. And I should use an approximation here because it's approximately equal to that. So we're approximately getting that 1 over x squared is equal to, let's see, f of 2 is 1/4. F prime of 2 is negative 1/4 times x minus 2. F double prime of 2 is 3/8 divided by 2 factorial. I would probably change the, so when I start simplifying this, I would probably write just 2 instead of 2 factorial. I'm going to have 3/8 over 2 times x minus 2 squared. And then f triple prime of 2 is negative 3/4 over 3 factorial, which is 6 times x minus 2 to the third. And depending on how much simplification someone was looking for, I might stop there. I might do a little more. So this is saying that 1 over x squared could be approximated by this third degree Taylor polynomial, and it would be not terrible. On the other hand, if we want the entire series, then we kind of need to do a different thing. So, right, I don't know what the next term is going to be without doing the same sort of work. So let's kind of go back and say, well, now we want the entire series. For f of x equal to 1 over x squared, still centered at 2. So here's some words of wisdom. When you're trying to find the entire series, you're looking for a pattern for the nth derivative. Because again, our formula is that f of x is equal to the sum from n equals 0 to infinity of the nth derivative evaluated at the center over n factorial times x minus the center to the nth power. The only thing we don't actually know is what this nth derivative is going to be in terms of n. That's usually what our job is to find out, which is usually the hardest part of the problem. Like the rest of this is not bad. We're just kind of throwing it into a formula, but finding what the nth derivative of c is kind of a pain. So what I would say is when you're finding this, don't simplify your derivatives. Let's take a look. So our function was 1 over x squared, x to the negative second. Our first derivative is -2 times x to the negative third. Our next derivative is, I'm not going to write 6, I'm going to write 2 times 3. So it's positive 2 times 3 times x to the negative fourth. And then the third derivative is going to be -2 times 3 times 4 times x to the negative fifth. And I think we can start to see the pattern here. If I do one more, the fourth derivative is going to be positive 2 times 3 times 4 times 5 times x to the negative 6. What I would observe here is 2 times 3 times 4 times 5 is 5 factorial. 2 times 3 times 4 is 4 factorial. 2 times 3 is 3 factorial. 2 is 2 factorial. And the 1 here is 1 factorial. So it looks like the coefficient of my derivative here is just going to be the next highest number factorial. So, right, if it's the first derivative, I've got 2 factorial. If it's the second, I've got 3 factorial. So I can make a pretty good guess that my nth derivative is going to be n plus 1 factorial times x to the negative n plus 2. And I need to deal with the alternating part. So when the derivative is odd, it's negative. When the derivative is even, it's positive. So it looks like I need a -1 to the n. Because if n is even, I'll get a -1 to an even power, which will be positive. So I think we're good to go. And then we're going to plug in x equal to 2. So my nth derivative of 2 is going to equal just n plus 1 factorial times x to the negative, times 2 to the negative n plus 2 times -1 to the n. And all of that is what we're going to put in for that right there. So when we try to write out what our actual function is equal to, we're going to say that 1 over x squared is equal to the sum n equals 0 to infinity of all of this over n factorial. So n plus 1 factorial times 2 to the negative n plus 2 times -1 to the n over n factorial times x minus 2 to the n. Kind of a lot. There's a couple simplifications I would make here. Specifically, n plus 1 factorial over n factorial is just n plus 1. So I would definitely rewrite this as the sum from n equals 0 to infinity of -1 to the n times n plus 1. And I would probably put the 2 to the negative n plus 2 in the bottom as 2 to the positive n plus 2, and then times x minus 2 to the n. That's our formula. It's kind of terrible. Hit me. Right here. So remember, oh, that's that's a good point. So when I'm finding what goes here, I'm taking my nth derivative and I'm plugging in the center value. So our center was 2. I plugged in 2 there and I got 2 to the negative n plus 2 instead of x to the negative n plus 2. So here's just my derivative as a function of x. Here's my nth derivative plugging in the center at 2, because that's within the formula here. And then I'm dividing by, so I've got all of that right there. And I'm dividing by n factorial, and then multiplying by the variable x minus the center 2 all raised to the nth power. Other questions, or still questions about this? I can talk more about this. I'm happy to say more words about this. This equation right here? Yeah. So again, I was taking derivatives, right? So I got down to like the fourth derivative and I started to see the pattern. I started to see that, oh, it looks like I just have 4 plus 1 factorial, or 3 plus 1 factorial, or 2 plus 1 factorial there. So that's where I'm getting my n plus 1 factorial. I can see that the power here is 1 higher than the number there, except it's negative. So I've got negative, well, that's n plus 1, that's n plus 2. So I've got x to the negative n plus 2. And then I needed the negative 1 to the end for the alternating part. And I knew it was n because I just checked. Right? If I plug in n equals 2, my second derivative should be positive. That checks out. If I plug in n equals 3, my third derivative should be negative. That checks out. So you basically, if it's alternating, you have to check one of them to make sure you're starting at the right sign. So then all of that, except now I need to plug in x equal to 2, right? Because the Taylor formula says you want the nth derivative evaluated at your center. So that's what I'm getting right there. I'm plugging in 2, I'm getting n plus 1 factorial times 2 to the negative n plus 2 times negative 1 to the n. And then finally, I'm taking all of that and substituting into the numerator of this summation formula. So I've got all of that as my nth derivative of 2 divided by n factorial times x minus the center, which is 2 to the nth power. And then after that, I said, well, there's a little bit of simplifying I can do. N plus 1 factorial and n factorial, we should always reduce that down to just n plus 1. And then I brought the 2 to the negative n plus 2 down to the bottom. That's just n plus 2. There was something else I want to say here. Yeah, I know there is. There's something else I know I'm going to say, but there's something else before that. No, I guess not. We could certainly be asked to find the interval of convergence here. So, interval of convergence, we take the limit n goes to infinity of the n plus 1 term over the nth term. We're going to get, okay, when I do interval of convergence, I really ignore the alternating part. I know it's going to go away. I'm just going to write n plus 2 times x minus 2 to the n plus 1 over 2 to the n plus 3 times 2 to the n plus 2 over n plus 1 times x minus 2 to the n. When I do that, I get the limit n goes to infinity of, let's see here, n plus 2 over n plus 1. We know that's going to just have a limit of 1. And then x minus 2 to the n plus 1 over x minus 2 to the n is just an x minus 2. And 2 to the n plus 2 over 2 to the n plus 3 gives us a 2 in the denominator. So we end up getting just the opposite value of x minus 2 over 2. I want that to be less than 1. So we have x minus 2 between 2 and negative 2. So x is between 0 and 4. Do we need to check the endpoints? Did the question say interval of convergence? Yes. If it says interval of convergence, we have to check the endpoint. So, okay, endpoint. So again, I'm going to check what I think is going to give me the non-alternating one first. So actually I have to be a little bit careful here, because if I plug in x equal to 4, that's actually going to still be alternating, because I'm going to have 2 to the n times the negative 1 to the n. So actually I'm going to plug in x equal to 0 first. Of course, I'm running out of room. Let's go down here. So check our endpoints. So again, here's what I mean, right? If I set x equal to 0, I'm going to get the sum from n equals 0 to infinity, negative 1 to the n times n plus 1 over 2 to the n plus 2 times negative 2 to the n. Negative 1 to the n times negative 2 to the n is just 2 to the n. So it's not alternating. So this is going to be the sum from n equals 0 to infinity of 2 to the n over 2 to the n plus 2 times n plus 1. I'm pretty sure this is going to not converge because 2 to the n over 2 to the n plus 2 is just 1/4. This is the sum of 1/4 times n plus 1. That's a pretty hard diverge by the nth term test. And even though the other one's going to alternate, I think it's going to end up diverging too, because it's not going to meet the conditions of the, I think it's still going to diverge by the alternating series or by the nth term test. But if we check out x equal to 4, then we've got the sum from n equals 0 to infinity of -1 to the n times n plus 1 over 2 to the n plus 2. And if x equals 4, 4 minus 2 is 2, so you've got a 2 to the n. 2 to the n over 2 to the n plus 2 is, again, 1/4. But now we've got the sum from n equals 0 to infinity of -1 to the n times n plus 1 over 4. And this also diverges by the nth term test. I guess they both diverge by the nth term test. So our interval of convergence here is everything from 0 to 4 exclusive of the endpoints. Sorry. So here's what I would generally say about power series. If you're asked to find a power series, you should always be trying to do it the shortest way possible. Meaning, usually, if I'm finding a Taylor series, so we use the word Taylor series, we use the word Maclaurin series, we use the general words power series. They're all kind of referring to the same idea of writing this function as a sum of powers of x. Taylor series specifically means we're centered around some point. We're writing it using this Taylor's formula. Maclaurin series just means the center is 0. That's literally all it means. Take the same exact formula for a Taylor polynomial and make the center 0, which it often is. That's a Maclaurin series. So let's actually look at an example. Find the Maclaurin series for f of x equal to e to the x. This one's definitely one of the easiest ones we can do, and it's definitely one you should memorize. It's going to come up all the time. And there's a few we should memorize. We'll talk about the end here. So let's see. My function is e to the x. My derivative is e to the x. My second derivative, oh yeah, I think I can stop. Right? All the derivatives are just e to the x, which means all of my function and derivatives evaluated at 0 are just going to be 1. Which is really nice. That means in my formula, my nth derivative evaluated to 0 is just 1. So when I start writing this, the sum from n equals 0 to infinity of my nth derivative evaluated at 0, over n factorial times x minus 0 to the nth, we're just going to get the sum from n equals 0 to infinity of, well, the nth derivative at 0 is just 1 every single time. That's going to be 1 over n factorial times x to the n, which is just 1 plus x squared over 2 plus x cubed over 3 factorial. It goes on and on and on. And that is what e to the x is equal to. And last class, we did talk about how the interval of convergence for this series is everything. So the interval of convergence here is negative infinity to infinity. The radius of convergence is infinity. So that means no matter what value you pick for x, this series will converge to e to that value, which is really nice. So, yeah, let's go this way. So what I'll say about this is often we then use things like this to compute harder Taylor series or Maclaurin series. For example, where'd my example go? Sorry, I lost it. 1 second. Oh, yeah, go ahead. Sorry. What was that? The interval of convergence? Well, it's not geometric, so the way we would do it is just like the way we would anytime. So if you're ever asked to find interval of convergence or radius of convergence and you don't know it right off the bat, because it's like we might, if it's geometric, it'd be like, oh yeah, it's -1 to 1. If it's not geometric, then we're going to go back to the ratio test. So I'm going to do the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times n factorial for x to the n. And when we reduce this or simplify this, we end up with just x over n plus 1. But then x is just a real number, and the denominator is getting infinitely large, so this limit's always going to be 0. And that's always less than 1. So no matter what value of x we pick, this series will always converge, which is why the interval convergence is everything. You got other examples that I really wanted to get to. Am I hiding anything from myself? Oh, there we go. Cool. Yeah. So here's why we want to memorize things like e to the x, or I will say sine of x and cosine of x, which we'll talk about in just a second here. But if I wanted to say someone said find the Maclaurin series for x times e to the x cubed. For f of x equal to x times e to the x cubed. Doing it what I call the long way, where you find a bunch of derivatives and try to find a pattern for it and then plug in your center, is really, really hard. I mean, think about it. If we start taking derivatives, the first derivative is going to be 1 times e to the x cubed plus x times e to the x cubed times 3x squared. And it's not going to get nicer, right? The second derivative is going to be worse. The third derivative is going to be worse. And the second derivative is going to be, I don't know, 3x squared times e to the x cubed plus that's a 3x cubed. So it's going to be a 9x squared times e to the x cubed plus a 3x cubed times e to the x cubed times 3x squared. That's not good. It's not going to be easy to then plug in 0 and find any kind of reasonable pattern. And the point is we don't have to. So instead of trying to do something ridiculous like this, we can manipulate known Maclaurin and Taylor series already. So we already know that e to the x is equal to 1 plus x. It's x squared over 2 factorial. It's x cubed over 3 factorial. It's really funny to me, by the way, that people like really don't want to write like 1 over 0 factorial plus x over 1 factorial. Like they just for those first couple terms, we don't write the pattern even though it's there. Right? Every time we're really dividing by the next n factorial. We just don't write 0 factorial and 1 factorial because they're both equal to 1. But they're there. So here's e to the x. Well, we can use substitution. I can say I'm going to replace x with x cubed. So e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on and so on. So e to the x cubed is 1 plus x cubed squared over 2 factorial plus x cubed over 3 factorial, and so on and so on and so on. This first one we know is the sum from n equals 0 to infinity of x to the n over n factorial. So here we're just replacing the x with x cubed. So this looks like it's going to be the sum from n equals 0 to infinity of x cubed to the n over n factorial. And then if I want to multiply the whole thing by x, I'm just going to multiply the whole thing by x. So then x times e to the x cubed is going to be x times all of that. 1 plus x cubed squared over 2 factorial plus x cubed over 3 factorial, which literally just amounts to multiplying every term in my summation by x. So it's going to look like the sum from n equals 0 to infinity of x times x to the 3n over n factorial. Or as I would probably write it in the end, f of x equal to x times e to the x cubed is equal to the sum from n equals 0 to infinity of x to the 3n plus 1 over n factorial. And 100%, anyone ever asks you to find this Maclaurin series, this is the way they mean for you to do it. They do not mean for you to take a bunch of derivatives and try and find a pattern. It's really kind of impossible to do, especially because for this one here, we're only getting every third power of x, right? We're getting x to the first and then x to the fourth and then x to the seventh. That means all those intermediate derivatives, like the second, third, and fourth one, are all going to be zero when you plug in zero. That's just not helpful, right? It's going to be way too many derivatives. You have to take 4 derivatives just to get to the next non-zero term. So definitely, if you see something that looks like a mishmash of a bunch of kind of functions together, this is usually the process where you take things we already know and we manipulate them to be something new. So that said, what Maclaurin and Taylor series should we know? We should definitely know e to the x. We should definitely know sine and cosine. So sine of x, let's do that one. All right, so f of x is sine of x. Oh, sorry, sine of x centered at 0. Or in other words, the Maclaurin series for sine of x. Someone could just as annoyingly say the Taylor series centered at 0. That would be equivalent, but Maclaurin series is easier to say. So we're going to take some derivatives. The function is f of x equal to sine of x. The first derivative is cosine. The second derivative is negative sine. Third derivative is going to be negative cosine. And then the fourth derivative, we're back to where we started. Fourth derivative is going to equal positive sine. So the nice thing about sine or cosine is after 4 terms, things just start doing the same thing over and over and over again. So if I'm plugging in 0, f of 0 is going to be sine of 0, which is 0. F prime of 0 is cosine of 0, which is 1. F double prime of 0 is negative sine of 0, which is 0. F double prime of 0 is going to be negative cosine of 0, which is negative 1. Finally, the fourth derivative, we're back to where we started. That's also going to be 0. So then the power series keeps going. 0, 1, 0, 1, 0, negative 1, 0, 0, 1, 0. I think I said too many zeros. 0, 1, 0, negative 1, 0, 1, 0. Yeah, okay, fine. So here's our pattern. So that means if I'm going to write out my Taylor polynomial sine of x, which is going to be the sum from n equals 0 to infinity of my nth derivative at 0 over n factorial times x to the n. I'm just going to add some terms. So I'm going to get my original, so I'm going to get 0 plus 1 over 1 times x to the first plus 0 plus negative 1 over 3 factorial times x to the third. And then my fourth term is going to be 0. My fifth term, back to being positive. It'd be positive 1 over 5 factorial times x to the fifth. And it just goes on. We can kind of start to see that we're only getting odd powers of x. So every even power of x, the derivative is 0. And they're alternating signs. Positive, negative, positive, negative. So this ends up looking like x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on, and so on, and so on. I do find it easier to think of this way. So whenever I think of the sine one, I'm just thinking, oh, it's all the odd powers of x. Not surprising if we remember that sine is an odd function. You only get the odd powers of x. And they alternate between positive and negative. And you're always using the same power as the factorial or divided by. And so that's equal to, I feel like the sigma notation for this is always kind of annoying. It's x to the 2n plus 1 over 2n plus 1 factorial times negative 1 to the n. 2n plus 1 will get us every odd integer. We're definitely starting at the right place. But I personally would remember this. That sine of x is equal to x minus x cubed over 3 factorial plus x to the 5 factorial, and so on, and so on, and so on. And I think it's worth checking on your own, but I think you should do it on your own when you have a chance. I will point out that the interval of convergence is everything. Check for yourself. Check using the ratio test. They will point out, just like the e to the x one, you're going to end up with x over something that is like a 2n plus something, and that'll eventually go to 0 for every value of x. So there's your sine function, and after knowing the sine function, we can make a reasonable guess at cosine, or we can even be smart and just take the derivative. So to find cosine of x, we're just going to take the derivative of sine of x, which is just the derivative of all these terms. Well, the derivative of x is 1. The derivative of x cubed is 3x squared over 3 times 2 times 1. The derivative of x to the 5th is 5x to the 4th over 5 times 4 times 3 times 2 times 1. Minus 7x to the 6th over 7 times 6 factorial. And so on and so on. And look what we get. We get the same pattern with all even powers instead. We end up with just 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so on and so on, which is the sum from n equals 0 to infinity of x to the 2n for 2n factorial times -1 to the n. The one thing I'll say about cosine, which is easy to forget sometimes, is it starts with a 1. It doesn't start with x squared. It starts with 1 and then minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. If it helps you remember, you could say that first term is x to the 0 over 0 factorial. So great. These, I would say, are probably the 3 main Maclaurin series you should be aware of. That's probably not true. I would say you should probably know the following. So Maclaurin series to know, or I should say series to know. The ones we just talked about. E to the x is 1 plus x squared over 2 factorial, and so on and so on. Sine of x is the odd powers. And cosine of x is the even powers. Couple other ones I think you probably, well, definitely we should know the 1 over 1 minus x. That's kind of the thing that started this whole conversation. That's just 1 plus x squared plus x cubed, so on and so on. And then I will be perfectly honest, I always forget this next one, but I'm pretty sure, I always have to work it out. The natural log of 1 plus x. Now, where do we start with that? I always have to look. So this is what I feel like you should know, but I don't know it, which is not very good. Not modeling good behavior here. Yeah, it's x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, so on and so on. These are probably the 5 most common power series, Taylor series, Maclaurin series that we encounter. Couple things to point out. All of these are centered at 0. So these all are Maclaurin series. And if we want to write the formula, this is the sum from n equals 0 to infinity of x to the n over n factorial. This is the sum from n equals 0 to infinity x to the 2n plus 1 for 2n plus 1 factorial times -1 to the n. Wow, can I get that? -1 to the n? Sure, maybe. Wow, that's terrible. Sorry. And -1 there is awful. Same deal for cosine. Got even powers, so x to the 2n factorial times -1 to the n. This one's just straight up the sum from n equals 0 to infinity, x to the n. And this one is the sum. Usually, so I wrote it a different way when we did it the first time, but most of the time people write this as the sum from n equals 1 to infinity of x to the n over n times -1 to the n plus 1. It doesn't need to be n plus 1 there to make sure we start with the right sign. The other thing I'll point out is these first 3 series have an interval of convergence that is everything. This next one here, the interval of convergence we've seen many times is between -1 and 1, exclusive of the endpoints. And this one here, I know we did it when we did it before. The interval of convergence is -1 exclusive to +1 inclusive. So not that you have to necessarily have memorized interval of convergence, just that it's good to know. These are the series I would say you should know, so that then you, when you're asked to find, say, the Maclaurin series or the Taylor series or something kind of wild, you can use some of this knowledge to not have to do all of that work that we've been doing. So let's see, let me give you an example here. Sure. So let's say someone said, oh, sorry, let me put it back up. Give me a moment here. I got a couple months, yeah. So let's say someone said, I want you to find the Maclaurin series for sure f of x equal to sine of x squared minus x squared all over x. Seems kind of funky, but it's not that bad. I suppose you could simplify this maybe, but I don't think I really want to. So I'm just going to start with the thing that's the complicated part, right? Sine of x squared is the only thing that actually really requires the Maclaurin series part. Everything else is just manipulation after that. So we know that sine of x is this thing. X minus x to the 3 factorial plus x to the 5th over 5 factorial, etc., which is the sum from n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial, -1 to the n. And I'm just going to replace x with x squared. The sine of x squared is just looking like x squared minus x squared cubed over 3 factorial plus x to the squared to the 5th over 5 factorial and so on. And I'm just replacing the x in this formula with x squared. So that's going to be the sum from n equals 0 to infinity of x squared to the 2n plus 1 over 2n plus 1 factorial times -1 to the n. And then I'm just going to, so here's a nice way to cut off the next term. I'm subtracting x squared. Well, that means I can just say, well, great. Sine of x squared minus x squared is just, well, I'm starting here now. So I'm going to get minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus the next term, which would be x to the 14th over 7 factorial. As far as the summation goes, I'm just cutting off the beginning term. I'm starting 1 later. So I'm starting at n equals 1 to infinity of x to the 4n plus 2 over 2n plus 1 factorial times -1 to the n. And then if I want to divide everything by x, I'm really just lessening each power of x by 1. So I divide everything by x, sine of x squared minus x squared over x. Well, I'm dividing everything by x. I'm going to get minus x to the 5th over 3 factorial plus x to the 9th over 5 factorial minus x to the 13th over 7 factorial, which as far as my summation goes, I'm just subtracting 1 off my power of x. That's going to be x to the 4n plus 1 over 2n plus 1 factorial, -1 to the n. I don't think you need to write out all these little terms here. I'm just kind of doing that to help see what's really happening here. If I was like doing this on a test or on a homework problem, I would be like, okay, sine is that, replace x with x squared, so you get that, simplify it out. I might look at this here to see that the first term does actually just cancel out when I write that out here. But I'd be like, okay, I'm cutting off the first term. There's another way to do that if it doesn't work out nicely like this. And then finally, dividing everything by x, I'm just reducing my power of x by 1. So I don't think you need to write out all these terms, but you certainly can to help you see what's happening. Long story short, when you're trying to find a Maclaurin series or a Taylor series or a power series for something that's complicated is looking, fall back and use the series we already know, and then try to manipulate them to look like the series you're trying to get to. No one ever means for you to start taking derivatives here and plugging in your center equal to 0 to try and find your coefficients. They mean for you to do it this way. I will say lastly, there are some functions though where we do just have to straight up apply the Taylor's formula because we can't really do anything else because it doesn't look like anything we've ever seen yet. So we'll talk more about that